Okay, guys, welcome back. This is the last class before midterm or before spring break. Excuse me, spring break. Um, Good to see everybody. And where we left off last time, we were right in the middle of what epoch are we talking about? Pleistocene. Yeah, good. We're going to see if we can get through the Holocene or into the Holocene today, because part of the Holocene experience, I do want to wait until after spring break to cover part of that. But let me just sort of reset where we are for a minute, right? We've been coming a long journey. What did I say in my email to you guys the other day? We've had 12 classes or something like that. It's hard to believe. So tonight's class 13. We've been talking about how all this land has come into being and how it's evolved and how it's sort of shaped and changed. It's been quite a journey, right? And I want to bring you up to sort of the modern day, and that's where the Holocene will enable us to do that. So the Holocene, which we'll start with at least by the Tuesday following spring break, will be designed to kind of say, okay, we're here, we've arrived. Now, how do we make sense of the landscape before us? Like, what are the ecosystems that we have? And that, of course, is important for how we think about species and species distributions and dispersal patterns, all the stuff you learn in most of your other biology classes. Where we left off then on Tuesday was we had just begun to talk about, okay, so we were in the middle of the ice ages. There were these long warm periods during the past 2.5 million years. And we said the really long warm periods occur at what frequency? Do we remember? About every 100,000 years or so. And what are those long warm periods called, Clayton? Interglacials, okay? And then we said that when there's a glacial period, sometimes the glaciers advance or retreat. What do we call the time periods when the glacials are thriving and flourishing and growing? What are those called? That's when they've reached their southernmost extent. But what is that time period, just generally speaking, when they're actively sort of growing and it's usually colder? Those are stadials versus interstadials, right? Now, when we get to the end of the Ice Age or to the end of the Pleistocene, and this also would have been true of the major transition points between glacial and interglacial periods, we would expect to see a major retreat of glaciers, okay? And that's what this map right here shows, which I showed you last class period, is at the glacial maximum, down here at the very bottom, those glaciers begin to melt and they go through a calving process, right, where they're breaking off icebergs and they're breaking off and they're melting. And then gradually over several thousand years, those glaciers retreat all the way back up to their modern day position, which is the area shown in white. Greenland, that's the modern day Greenland ice cap. There's a little bit of ice cap as well on some of the adjacent lands of northernmost Canada. And you can see some ice cap in parts of Alaska there. So generally speaking, that's been sort of the retreat of glaciers all the way up until the modern day, up until the Holocene. What we want to understand with today's lecture is what was that transition period where we were coming out of the Pleistocene, getting ready to go in the Holocene? What was that like? It was actually a time of great instability. It was a time of great extinction and loss of species diversity. And so we want to and it was also a time of opportunity. About this time, actually a few thousand years before, is when we see the first people cross into North America. And of course, South America. So the entire Western Hemisphere had been without the human species ever in the course of history up until the late Pleistocene. So that has a major sort of worldwide, world-changing effect to all of a sudden introduce a species as impactful as the human species. So the end of the Pleistocene is a critical time period. Then I left off, I think the last slide was we were just talking about equating the retreat of glaciers and the melting of glaciers with other kinds of phenomena, like the rising of sea levels. Okay, so remember this image here, we showed what happens, for example, when you take the retreat of glaciers shown in the area blue, which would be at about 21,000 years ago. Those areas in very darkest blue, that's in southern and eastern Alaska and adjacent Yukon, Canada. That's where the glaciers were. By 14,000 years ago, the glaciers had begun to retreat really to the east, and that's the area shown in light blue. Just that little bit of retreat, which is only a few hundred miles at best, or a couple hundred miles, that alone was enough to raise sea levels in the same time period between 21,000 and 14,000 years. So just a period of 7,000 years, it was able to raise sea levels enough to where it drowned the Beringian land bridge, the land bridge that connects Russia to Alaska. So that's what we see here going from brown to green. Brown shows the area where sea level would have been at 21,000 years versus at 14,000 years. So you can see that the ocean would have covered that that past, and then that's what the sort of AI generated image on the left is intending to show, is that space between Alaska and Russia. Okay, so the ice begins to melt, right? That is a big deal for life in North America. It's a big deal for life anywhere. Let's take a look at some of the kinds of other changes we would expect to see, not just the sea level, but let's also look at the effect of having less ice covering the land. Well, that ice weighs a ton. I mean, it weighs a lot, right? If you look at this diagram here, notice how the weight of the ice depresses the land underneath it, because some of that ice was 3,000 or 5,000 feet thick. It literally was a mile thick of ice. And it covered the entire northern half of the continent, right? All the way down to northernmost Kentucky. So when you have that much weight of ice, it depresses the continental crust beneath it. And what happens is it's sort of like pushing down on like maybe an ice cube that's floating in water. When you push down on it, it is pushing down on the mantle underneath the crust, that molten mantle. Then the mantle, because it is liquid and molten, is actually pushing outward to both sides. And that's what you see these flows of the arrows on either side here to the left and right. As the loaded crust sinks down, the mantle flows to either side. And what that does then is it creates a bulge or uplift effect on the edges of the ice. Where you don't have ice, those areas then sort of rise upward. And that's what it's showing here, that effect here, these peripheral bulges that flex upward. All those things can, well, let me ask it to you as a question. What is the impact of having those landscapes that are beginning to bulge upward? What would you expect to be happening in these areas where the land is rising on either side of the ice? Okay, talk to us about that. Increased erosion rates, because how are those connected?
Level higher they get, the quicker they'll erode by water and so maybe expect to see, once the ice is gone, leveling or still left over, depends on the rock.
Okay, so yeah, just a good rule of thumb is this: if you have uplift by some force, then you have downcutting working in opposition. So increased erosion, increased incision of stream valleys, increased formation of river gorges and hollows and canyons and all these kinds of topographic features, okay? Now, what happens if the ice melts away? Well, when the ice melts, the land underneath it is able to rise again. Remember, it's floating over molten magma. And that magma in the mantle flows back into place where it was displaced previously. It is actually more dense than the continental crust above it. So it's able to have a push-up effect, an uplift effect on that land. And then you would expect in those bulges on either side to actually collapse downward a little bit. So they might actually drop in their altitude. Whereas the area that is in the middle will have a rebound effect. So it can actually uplift land that was previously submerged under ice and maybe even underwater. It can rise above sea level, or areas that were, like the continent of Eastern North America can then begin to rise in response to that ice having melted. So this seems pretty ludicrous, to be honest with you, right? The idea that ice could have this depressive effect, but if you take the ice away, it can have an uplift effect. Matthew?
I think they're all from the sheer force of the entire glacier, because water is heavier than, or it's heavier than ice. So it's like the full force of the glacier just pushing down on it, holding it in place, and when it melts away, the water doesn't have that.
Well, I guess what I mean to say in this particular diagram is a little misleading, right? Because what we're saying here in this case is I'm showing you visually an example where there's a glacier that is over a continent, let's say. And if we just simply took that away, then you might expect that glacier to just simply rise and the continent, glacier melts and the continent rises. This is a little bit confounded because you've got a sea that's depicted in the lower right. It doesn't always have to be a sea on top of the land. So if we're talking about Michigan, let's use Michigan as a specific example. You wouldn't necessarily have this, right? You would have a glacier that is retreating back. There would be no seas or anything standing on top of the land in addition. The land then is just going to rebound after the glacier melts. You can also have the rebound effect, though, as a sea pulls away. So remember we talked about that Central American, the intercontinental seaway that is stretched from Alaska down to the Gulf of Mexico. That also has a lot of weight. And that has a depressive effect on the crust beneath it. Likewise, when that epicontinental sea retreated to the north and south, the land under was able to rebound as well. That's really what this is talking about. It's really two different examples, one where a sea covers land and one where a glacier covers land. Clayton?
When the land rebounds, does it just return to its previous level, or does it overcompensate and oscillate over time until it settles?
That's a good question. So we now have been, let me throw this out and I'm gonna get back to answering you with the next slide. How long have we been sort of without glaciers covering the United States? I'm not talking about Alaska, but like the lower 48. About how many years have we been at least? No, so remember those glaciers, remember we said, let me ask it another way. How far back in time do we have to go before there was a mile of ice over Cleveland, Ohio? Remember that? I gave you that question. 18,000 years. So really recently, right? So if we go back to this map here, at 18,000 years, we had glaciers covering Cleveland, glaciers coming down to New York City, glaciers covering Chicago. So as those glaciers retreated and pulled back to the north, that means then that, okay, maybe at 15,000 years, there were glaciers over northern Michigan and over Vermont, right, up here. Maybe by 13,000 years ago, the glaciers were covering northernmost Minnesota and northernmost Maine. Maybe by 11,000 years, they had completely withdrawn and were not covering any of the lower 48 United States, but they were in Canada. From there, we go back 11,000, 10,000, 9,000, 8,000. You get the picture, right? Until eventually they're pulling all the way back up to here in, say, 2,000 or 3,000 years ago. And then they're pulling all the way back almost to Greenland by just a few hundred years ago. So the reason I was asking that question is to show that not a lot of time has gone by. 15,000 years, let's say, before they exited the United States. So I'm gonna put a question. Let's assume that it was 15,000 years that glaciers last covered the lower 48. If that's true, then you would expect what to have happened with the sort of the elevation of the United States, or the general altitude of the landscape. If you take the glaciers away, what's happened? Yeah, you would expect large parts of the lower 48 United States to begin to rise, right? How long would that last? How long would that rising following the retreat of glaciers, the melting of glaciers, continue? Would it last hundreds of years or thousands? Any ideas on that? Yeah, so all right, and going back to this map, right? If the glaciers took 10,000 years to recede completely, then what's the lag effect with the amount of time it takes for the land to rise? So it's been almost 18,000 years since they were here. Are we still seeing land rising in Tennessee today from the retreat of the glaciers 18,000 years ago?
I think that because the rise of the mantle under, like, we're not waiting on convection currents to move continents. It's a much smaller scale fluid dynamic with that constant pressure from underneath. So I'm tempted to think it's happening over decades or centuries.
So you're thinking it's a quick rebound effect, right? Anybody have any difference of opinion on that? Anybody online have any difference of opinion? Is that a slow process on the order of decades to hundreds of years? Or is it a long process that takes thousands or 10,000 years? What do you think? Okay.
This sounds like a crazy question, but since it's all floating on the mantle, would it not seek the same level as the uplifted land around it?
Help me out with that, Laura. Clarify that just a bit.
I'm thinking of the rebound of the land, right? But I'm also thinking of the uplift on the margins, right? And with the land that was suppressed, would it rise up to meet the other land?
Well, keep in mind the land that is
underneath on the mantle level, it's all.
Yeah, right. Well, that's a good question. And because the land is not fluid, right? It's not molten like the mantle is. Its ability to respond and move is not going to quite act the same as the mantle underneath. But I get your question. So basically, would it rectify itself to come up equal to where the land that had been previously uplifted was?
Yeah.
Well,
yep.
Without confusing it much more, let me kind of reveal what the answer is. All right. So as of today, there are still a massive amount of rebound taking place. And we can measure it on a yearly basis. Organizations, agencies like the U.S. Geological Survey especially would be the ones doing a lot of this work, and probably the equivalent agencies in Canada. So these lines in red show the area that is largely north of that green line. Who knows what that green line is called from there north? Where the glaciers kind of just scraped everything? No. The zone of erosion, right? The zone of erosion. So above that line, what you see in red are arrows indicating the relative amount of rebound per year in millimeters. Think about that. 5 millimeters per year is shown there by sort of the legend. But take a look at some of these areas, like right here over Quebec, Canada, or up there on the northeastern coast of Canada. Some of those places are rising by a centimeter to maybe as much as 13, 14 millimeters per year. That's that much. That's how much it's lifting up per year, right? almost maybe equivalent to like your pinky nail in amount of rise per year. Now, in comparison, look below the zone of erosion down into the region we call the zone of deposition. And notice there, the land is actually sinking. So places like Kentucky and Ohio and Iowa and over on the Atlantic coast like Maryland, they're all actually going down. You can sort of imagine this like a seesaw effect, you know? Imagine that for a long time with the weight of the ice, it was very heavy and it was kind of tilting down the northern part of the continent. But as that weight has been released, it's sort of steadily righting itself. And so the northern half of the continent is like my left hand. This would be Canada and Alaska and northern United States is actually rising every year. And the southern part of the continent, like Kentucky and Ohio and Tennessee and Maryland, is going down. And so we actually have a seesaw effect, and that can be measured every year. What that means then is which of these areas should we be experiencing the most amount of land erosion currently? Where should we be seeing incision of river gorges and those kinds of things? Up north in the parts of Canada, that's where we expect rivers to be cutting down into their channels, into their beds. In contrast, though, in places like Tennessee and Kentucky and Ohio, what would those rivers be doing if they're not actively down cutting? They're depositing. And that is an important term. We're going to come back later after the midterm and hit. It's called aggradation. Aggradation or a grading. Those rivers like the Cumberland and the Duck River and the Harpeth River have been aggrading for much of the Holocene. They've actually been building up their floodplains. And I'll give you a good example of that right here with this point. I had a friend of mine, I met this guy one day and he said, hey, Dwayne, you're from down in southern Middle Tennessee, aren't you? I said, yeah, I grew up in Giles County and lived in Murray County for a while. He said, oh, you do any fishing? I said, well, I've never been a big fisherman. I love botanizing too much. I can't sit still for, to fish. Hell, I always just want to go look at plants. He said, well, I got this place down on the Duck River in Murray County and a beautiful little private property overlooking the river. You should check it out sometime. I said, oh, yeah, we got to just, making small talk, right? And I said, yeah, hopefully your farm wasn't too badly affected by those big floods we had a few years ago. He said, strange you mentioned that. He said, I had this campsite down by the river and I built this little deck and I put a grill there. And he said, the grill's like 3 or 4 feet tall, right? You'd sit there and cook you some steaks and the grandkids are swimming over in the creek and everybody's, somebody's playing horseshoes over here. He said, but the strangest thing happened. He said, I put that grill on this very low deck that I built that was like 6 inches off the ground. And we had some lawn chairs and stuff sitting out there. He said, after 2 or 3 floods that happened like 2 years in a row, he said, you'll never guess what happened. I said, it washed away your grill. He said, no, I had that grill anchored in just fine. It didn't wash it away. I said, well, I'm not going to guess what happened. He said, there was so much soil deposited that it actually came all the way up and buried my grill to where I could only see the top 3 or 4 inches. I said, really? I would never have guessed that, right? I sort of, was trying to stretch my brain and think about, well, how could that much soil have been deposited? And in part, it's probably because there's a lot of silt in the river from excess soil erosion these days. But another factor, it's not perfectly an example of it, but the more I read and the more I dug, the more I realized that the Duck River and the Cumberland and the Harpeth have been aggrading. They've actually been depositing. Some of that over the past 10,000 years is due to this rebound. And by the way, we call that isostatic rebound. That's the impact of losing this tremendous weight of ice and the rebound effect of the land. So in our case, though, we're not rebounding. The land is sort of sinking, and therefore the rivers are able to actually build up their floodplains rather than erode them down, which is happening up north. You might be thinking, well, why in the hell did you just spend 20 minutes talking about this, Dr. Estes? Well, I'll tell you why. Because these kind of factors are important in other classes that you have. For example, if you're talking about the evolution of fishes in ichthyology, it's real important to understand isostatic rebound, because then you can have an appreciation for fish evolution over the past 2 million years. You can understand as rivers are forming and new tributaries are evolving and cutting down in their drainage systems, channels can become isolated, and one lineage of fish can be divided into two, driving speciation processes. So it's really important that you have a fundamental understanding of how these are connected, because they are really critical to answering questions in biology and ecology. Now, we can see the evidence of this uplift effect from the rebound after isostatic rebound. Just take a look at the northern coast of Canada, for example. This shows what we call is a layered beach. And so every year with the land rising up out of the sea, you can see those are old coastlines, right? And now, as you would expect, with that uplift effect comes what? Down cutting. And so this little diagram that I've got here, you can actually see some of those incisions of small channels that are beginning to develop in that coastline. And so uplift leads to down cutting. It leads to channels and ravines and stream drainages and stream valleys and canyons. And that's what helps to drive a lot of the topography and land dissection that frankly governs a lot of our modern day landscape. And this has been happening for millions and millions of years. All right, any questions about that? It's pretty cool, right? That's one of my favorite examples actually in this class to talk about. I think it always kind of comes as a surprise to some students. Now we can look here to localized examples in Tennessee and see the effects of this down cutting. This is over on the Tennessee River. By the way, you can see the same thing at Land Between the Lakes. Everybody knows where LBL is, right? There's a few places, if you were with me and we were driving through LBL, I'd be able to point out to you, hey guys, look quick, look there on the left. There's a gravel deposit that sits on the top of the highest ridge in LBL right on the main highway. And if you know what to look for, this little outcrop of gravel isn't just typical gravel. It's actually 2 to 3 million year old Pliocene to early Pleistocene gravels that are river gravels. Now keep in mind, this is on the top of the ridge. The river now is 200 or 300 feet below and to the west over on the Tennessee River. So it begs the question, how do these deposits of riverine gravels get on top of the hill? And we know that they're roughly 2 to 3 million years old because that's how radiometric dating has aged them. Well, what that means then is what's the inference? How would you interpret that? Yeah, it used to be that the river was at that level, right? And what has happened? The rivers have incised in the landscape. They've cut downward so that now the river has dropped 200 to 300 feet and has moved locations. So that's what we see right here. Now in the orange highlighting, these are what we call high level Pliocene Quaternary aged alluvial deposits. These are, and they do form an unconformity because these very young gravel deposits sit directly over top of Silurian or Devonian age limestone. So there's they go from 3 million year old rock to like at least 300 to 400 million year old rock, and everything else in between is missing. So there's an unconformity. Here's as you can see from this annotation on the Google Earth map, those gravels are at an elevation of about 490 feet above sea level, but the river itself is at 360 feet above sea level. So the river then has dropped, 130 feet in about 3 million years, 2.5 to 3 million years. So think about that much change with the river, the biggest river we have, like the Tennessee. Now, of course, do we really know those river gravels came from the Tennessee River? That would require additional investigation. So you don't want to get locked in and just assuming that things, just because there's a river nearby, that those gravels belong to that river. Let me illustrate this on the board and I'll show you what I mean. So what we're talking about here in terms of location wise, I'm gonna turn this light on, I think. Here's Clarksville, and here's Nashville right there. Let's see, I think, let me see if I can turn this on for my friends here online, just so they can see my video. Yeah, so we've got Tennessee here. Here's Clarksville. Here's land between the lakes, National Recreation Area, right? The Tennessee River, which comes down out of Knoxville and Chattanooga, makes its way through northern Alabama, curves, and comes up and runs into the Ohio River, right? And these gravel deposits that I'm pointing out occur in just a few sporadic places along the tops of the hills in some of the highest hills, especially on the eastern side of the river. Now, it might be easy to assume that those gravel deposits belong to the Tennessee River, or what we call the Paleo Tennessee or the ancestral Tennessee River. But you don't want to get locked into thinking that completely. In fact, I think for these, you might even be wrong. In part, people who study stratigraphy, right, the rock layers, they can look at those deposits and look at things like the tilt of those layers, the orientation of the gravel particles, the orientation of the beds of sediments and gravels within them, and they can determine the direction of flow. And it turns out that a lot of these gravels up in here and some other gravels are actually to the east of Nashville, near Cookeville, Tennessee, and over near Sparta and near Gainesboro, Tennessee. And then there's a whole bunch of gravels that cover broad swath of western Kentucky, out here near Murray, Kentucky. It turns out these gravel formations are called the Lafayette gravel. It's the Lafayette Formation. And they're not just like loose gravels that are like just, like a gravel bar when you visit a river. They're actually concreted together as a conglomerate. So very much like this type of rock that I've got over here. Let me pass this around. In fact, you'll be glad to know this is a unit of the Lafayette gravel that I picked up from my place. So notice that the larger rocks are water worn, but then they're concreted together with a very heavy rock that has a lot of iron called ironstone. And that's a mineralized sort of rock that helps to form this conglomerate formation. But what the general consensus among geologists is that there actually was a river that didn't flow where you see it today, but instead it was a river that flowed probably in that direction. And all these gravels here, and at one time that river actually might have flowed broadly over this. And so it laid those gravels down, a very large river flowing from east to west. So even though it's adjacent to that river, you cannot assume they actually belong to that river unless you have direct evidence of that. So what's the point of this part? The point is that the melting of glaciers caused isostatic rebound. Isostatic rebound for a time, especially when the glaciers, I shouldn't say when they melted, when the glaciers were depressing North America, it was uplifting the Southeast, right? So during the Ice Age is when this area probably experienced its greatest incision. This area would have been uplifted like that seesaw effect. When the glaciers were weighing down, Tennessee would have gone up. But now that the glaciers have retreated, Tennessee's gone down, okay? So when the glaciers were there, this area down cut, and whatever rivers would have existed are now long gone, and the only way we have evidence of them are these scattered gravel deposits that are found on the very tops of some of the highest hills. Any questions about that? How cool is that? That's pretty cool, right?
That's way cool.
That's way cool. Yeah. And if you go to LBL, if anybody has ever wanted to go out there, I probably couldn't even give you GPS coordinates to where that formation is. But if I were there, I'd be like, hey, watch out, guys. Here it comes. It's on the left. Check it out. I pointed out to my family so many times and they're like, who cares? I'm like, it's 3 million-year-old river gravels. Don't you care? Sorry. Okay, let's fast forward and look at how we can use this sort of information to judge, again, the downcutting of landscapes. Here's another example. Let me turn the light out here. Here's another example where we can apply this sort of same information. This is up at Mammoth Cave National Park. And so you have the stream valley of the Green River that flows right through the park. And we can actually age the valleys themselves based on the terraces that the river forms, right? So as the river is cutting down, it is creating shelves or like natural terrace features in the valley. You can see it right here. Here's the immediate floodplain, right? And then you kind of come up, and this terrace then is the old floodplain of the river. We can ask the question, well, how long ago, if the river at its modern day is at its lowest point in the floodplain, how far back in time do we have to go until the river was up at a slightly higher level where that terrace is? We can date those. So geologists can date those using a variety of approaches. And it turns out those terraces are between 700,000 and 900,000 years old. There's a lot that goes into that that's beyond the abilities of this class to impart to you. But again, this has a lot of bearing on how we view the landscape and evolution of species, migration of species. It's important to know these kinds of concepts. Let's look at another example. This is over in East Tennessee, and there's a group of plants called rosemary bushes. This is not like your rosemaries you grow in an Italian garden. These are southeastern rosemaries that are members of the mint family, the genus Conradina. And there's 6 species of rosemaries in the southeastern U.S. That's where the entire genus is located. 5 of those 6 species that you see there up in the box in the upper left, all of those except the one with the red box around it occur in Florida and southernmost Georgia and Alabama, or southernmost Alabama. So they all occur down here. Several of these are really narrowly endemic species. One of them only occurs near Panama City, Florida, nowhere else on Earth. One of them only occurs south of Orlando, Florida, nowhere else on Earth. And then there's a species that's Appalachian. It's a cousin. It's the Appalachian cousin, right? It's found in a collection of counties up here on the Cumberland Plateau in eastern Tennessee, one county in Kentucky. And one of the similarities, these little shrubs are about 1 foot tall and they grow in pure sand. So like imagine sand dunes of Florida. What's the nearest thing to sand dunes in Tennessee? You're looking at it right there. These are down in a really deep canyon on the Cumberland Plateau. And here you've got these plants growing in deep sand, weathered from the surrounding sandstone. But yet these little shrubs are sort of a leftover from a past climatic period. And all their cousins occur way down here in Florida. It's like having a little bit of a sand dune in Tennessee. We don't exactly know when or how they got there. But one hypothesis we could test, right? And this is the advantage of being able to couple this information. If you have geologic information at your disposal, then think about what you could do with that as a biologist. You could test it genetically, right? You could form hypotheses and you could predict, maybe you might predict based on what you know of the geology that these species under a warmer past climatic period, maybe during a warm interglacial, let's say 200,000 years ago, maybe these ranged farther north, or one of the species ranged farther north. And maybe that species became fragmented during a past cool down period. So those species mostly pulled back down, except one stayed put over Tennessee and in a sandy environment. And then as the river began to cut down during the Ice Age because of the isostatic effect, as it cuts down, those populations sort of follow these open sand dunes along the river's edge. Maybe. It's a hypothesis that could be tested, particularly if you had genetic evidence and you could evaluate things such as a molecular clock analysis and do like divergence times to look at how far back in time do those genes separate from each other.
That's the same place you can find cactus stuff.
In some of these areas, yes, there are cactus. Yeah. And there's other species too that are more common in deep south areas. There's actually a whole collection of species. So that's what it looks like in Florida with these habitats. You saw the Tennessee examples. Again, maybe you had at one point in time this sort of more widespread species. You can imagine it becoming fragmented with climate change. Now imagine those rivers, because you have to explain these things somehow getting down into the bottom of those deep canyons, like at Big South Fork National Recreation Area. Maybe it sort of rafted its way down, not by, those seeds jumping off the canyon, right? Not by a bird taking these seeds, because these things are not bird dispersed, but by imagining something like as these canyons are cutting down, imagine that habitat one time being present on top of the plateau. And then as those streams incise down through down cutting, that habitat opens up. And as they continue to deepen and widen and cut down and form in the canyon, maybe that species migrates its way down into its modern position, 500 feet down the bottoms of these canyons. Okay, all that's hypothetical, but it all can be subject to testing. And importantly, it just highlights the need to be well-versed in geologic forces so we can inform our ecological and biological. Okay. Now, take a look here at this is remember we talked about meandering river systems? We talked about one of the ecoregions of Western Tennessee where the rivers just kind of do like this. They meander back and forth. They're swampy. They have, they're called a meander belt. The Lust Plain meander belt is what we call it. And then in the Mississippi River, we talked a bit about the northern Holocene meander belt ecoregion. So if you look here on the upper right is the Hatchie River just east of Memphis, and it shows a typical swampy river system. And one of the things that you'll notice, we actually pointed this out a few lectures ago, are those oxbow lakes. Remember that? Where the river has kind of cut itself off. But if you look at other rivers today across parts of Tennessee and Kentucky especially, you see that they have this also meandering looping pattern. And the only way you get that is if that river started out as a swampy river. That's really the only way you get a meander belt with oxbows is if it was swampy historically. You don't get it on the side of a mountain. Those rivers go straight down, boom. So the implication then is that this river, which today is deeply entrenched, like the Green River was of Kentucky that I showed you with that 700,000-year-old terrace, that while this river is entrenched today down in the bottom of a hollow, it wasn't always like that. And at some point back in time, it was probably flowing across a swampy, flat upland plain. Some force caused that river to begin down cutting. What do you know enough about now to be dangerous to say probably initiated the down cut? In order to have down cutting, you need to have what? Uplift. So what are the two sources of uplift that you're now aware of? Actually, you could say three. Give me the three sources of uplift. Isostatic rebound, yeah. You can have tectonic forces where Africa's colliding and subduction forces the land up. There's one more. The mantle plume, right? You can have a plume of molten magma, a bubble basically pushing up under the continent, forcing the land to rise. So those are the three. And which one is responsible for this? We don't know exactly. And that's a little bit beyond our discussion, but I wanted to point this out. Now, take a look at when we combine this with evidence from the Gray fossil site, where we have an amphibious rhinoceros that's more like a hippopotamus than anything. And we have alligators. It's warm. You can begin to see that we had conditions in Northeast Tennessee in the Pliocene and latest Miocene that suggest that swamps and wetlands were quite common in Tennessee. So maybe we would have had the conditions necessary then to support this river being very swampy. Right? This is the Wolf River over in Pickett County. By the way, that river in the bottom is the Red River. Just, this is about 20 miles northeast of Clarksville, where this landscape is today, as it flows across the Pennyroyal Plain. This is the town of Keysburg, which is up in, right over the Tennessee-Kentucky line in adjacent southern Logan County, Kentucky.
But those fossils were from the gray fossil site, right?
Yeah, exactly. The
Okay.
only reason I put these in is just to show you that we could have had the right kind of biological evidence 4 to 7 million years ago to support swampy conditions being common in the region. Right? A swamp dwelling
Gotcha.
rhinoceros and an alligator.
Yep, gotcha.
Now, this is another river that's also just south of the Tennessee-Kentucky border, but this is over about 75 miles northeast of Nashville. This is called the Wolf River up in Pickett County, Tennessee. And one of the things you can look at many different rivers. Look at the Kentucky River in Kentucky, the Green River of Kentucky. Here's the Wolf River, and they all have this similar meandering pattern, and they all have oxbows. Look at those abandoned river channels right there. That tells you those old oxbows, and they're overlaying each other. Look at this. This tells you that that was an ancient meander belt before this river was forced to begin to cut down into the pure limestone that forms its bed. Look at that. There's one. There's one. Pretty cool, huh? Now, let's throw into this a little bit more evidence for this downcutting force. Recently, there's been a slew of studies that have looked at caves over in the region around where the Cumberland Plateau is near Cookeville in Sparta, Tennessee. So over there, you've got these sort of, and this is Mammoth Cave up here, by the way, in the upper right. But in this area where you've got this plateau and you've got this escarpment, underneath that, you have caves inside the hill system, right? It's all limestone and all that stuff. Researchers have found out when you go into those caves, how many of you have ever been inside of a cave, have done some spelunking, okay? I'm too scared. I'm just not a big cave guy myself. But, you know, they always tell you when you're caving. Obviously, I've been on like a professional cave tour, but I'm not one of these daredevils that likes to go just hanging out in caves and stuff. But if you ever go and you're going to take like an official cave tour that sort of goes to a back channel, they'll always tell you like, wear your old clothes, prepare to get muddy, wear some old boots, right? You may come out just covered in mud from head to toe. Where do those muds come from in some cases? Have you ever stopped to think about that? Right. That's why this class is stretching your brain. Well, some of those muds, my friends, come when rivers flowed at different levels. Okay, so let's take a look at this diagram in the upper left, just to make it as a starting. Notice here that the river is flowing across a relatively flat plain. It's meandering, right? And it's got bends in it and stuff. As the river cuts up against the face of this bluff, those river waters are eroding into that bluff face, right? Maybe there's a seam of shale rock that it is easily able to erode out. Maybe the rain waters or the acids in the river water are able to carve a cavern that is at the same level as the river. Okay, that's what's happening here. That river then carves a cavern and it forms a cave that is completely flooded. That entire chamber is flooded. You would not want to go into that cave unless you're, wearing scuba gear. But let's watch what happens over a few 100,000 years or a few million years. Can you predict what's going to happen? Exactly. With downcutting through some force of, let's say, having a glacier sitting over the northern half of the continent, it's going to create the uplift effect needed to cause the rivers to downcut. The rivers are going to cut down to a new base level, in which case they're going to form a new floodplain, and it's going to leave that old cave that was flooded high and dry. Now, I ask you again, where did the sediments come that are inside the cave that they tell you to be wary of when you know you're going to get muddy. Yeah, many of these sediments were washed in as part of the frequent flooding of those caverns when the river simply carried sediments into that cave system. And so these are called paleo sediments. And boy, they are wonderfully rich in information. Now, I cannot do this justice, but I'm going to give you my country boy layman's terms approach, okay? There is a technique of dating that is very precise. We've all heard of carbon dating, right? Radiometric dating, dating with uranium isotopes and stuff. There's another kind of dating, and I have forgotten the name of it, but it doesn't look at things like half-lives, right? With carbon, we're trying to use half-lives to estimate, what percentage of a given isotope remains, and therefore you know the age. In this case, what we're talking about is there's a dating approach that can tell when sediments or rock particles were hidden from the sun. Okay, so if sediments were last exposed to sunlight at, say, 2.5 million years ago, and those sediments get washed into a totally dark black cave system, they now are out of the rays of the sun. There is a dating process, and I'm hoping somebody will remember what it's called because I can't, that can precisely date when those sediments were hidden from the sun. That's a pretty cool dating approach. And I'm going to find out what it is so that I can tell you. I should have known that. And I apologize. What is it? That's not the word I remember. I'm sure it is, but it has a very specific term. Maybe see if you can find it, Matthew, maybe on break or something. I don't want to distract you. But anyway, these are paleo sediments. And it's from these that we can age the cave systems, okay? Like this one right here, that's an abandoned cave system. So let's watch what happens as we go forward. Now, notice here at level B, once the river begins to drop, we're forming a terrace where that former base level of the river was. We drop down now, we have a new bluff, we have new floodplain. There's those abandoned gravels. That explains those gravels up on the summit of the ridges at Lamberton Lakes by the same kind of process of downcut. But the river now is going to form a new level of the cave system, level B. That's going to be flooded, but level A is a dry cave at this point, okay? And then we can continue to see the downcutting happen, and then we may go down at various other levels so that today we can go to places like the Cumberland Plateau Escarpment, and we can find 5 or 6 different levels of cave systems, all of which have their own paleo sediments, all of which can be dated, and we can then understand when did rivers last flow across the base of the plateau, and we can understand the evolutionary history of the landscape. How can this be used in a biological context? Think about our program here at Austin Peay, and think about some of the research and classes that you've had. How might this inform some of the work that's being done here? Any ideas? What kind of species that might people here at Austin Peay be studying that could really benefit from this kind of knowledge? Bats, bat evolution, right? Might be handy. What else? Yeah, cave fish, maybe some darters, cave salamanders, cave crayfish, right? Lots of cave insects, cave isopods, a bunch of types of macroinvertebrates, or invertebrates in general. So yeah, this is a very helpful line of, and by the way, these papers are all fairly recent, like as in the past, probably 10 years or more. It's a pretty exciting area of science to read up on. Now, I'll just summarize and we'll conclude on this point. I'm going to go for about 5 more minutes, then we'll take a break.
Theo's got your answer there.
Oh, Theo's got the answer. Let's read it. Hang on. I knew somebody come up through it. Yeah, it's sediment light dating technique is called optically stimulated luminescence. This was also used to date the pimple mounds. Remember that Theo told you about? Good job, Theo. Thank you. That's still not the same terminology that I remember reading. I'll have to look up the term that I remember. All right, let's go just about 3 or 4 minutes, and then we'll stop for a break. So let's take this full steam ahead. Now, this is from the same paper where they dated these various they dated these various caves, okay? Now, this is not very helpful to you if you don't know where you are, but Nashville would be like right over here to the west of the word Cumberland. Where you see the Calf Killer, the town of Cookville is located about where that word Calf Killer is. And then if you're familiar with like Jamestown, Tennessee, or Pickett State Park would be up here just to the east of the word Obie and Wolf River. The Cumberland Plateau generally is sort of moving right down through this region, or is located through about where those dates are given. The stars here indicate specific caves that were sampled, okay? And you can see then along the tributaries to the Cumberland River, like the East Fork Obie River or the Calf Killer River, those different cave systems indicate sort of how far up the river they are from from their mouth. So let's take a look here, for example, at the East Fork Obie. The farther you go up this way, the oldest cave is at the top of the watershed where you would expect. Right, that's the first one to form. That'd be your level A cave. It's highest up. 1.8 million years plus or minus 300,000 years. If you go down from there, 1.64 million years, 1.45 million years. You've got similar dates then are shown on some of these other river systems. So we can kind of gauge the age of these caves. As how long ago was there a river flowing against that escarpment at that point in time? All right, just to conclude, how is this really most beneficial? Let me hide this chat box. Let's take a look at examples of this phylogeny, right, where researchers have taken the DNA out of what they thought was one species of darter called the bar-cheek darter complex. This little fish right here in the lower left called Ethiostoma basilarii. They went out and they sampled this fish from 6 different river systems. They got some from the Barren Fork River, the Collins River, the Calf Killer River, Cane Creek, and the Rocky River, all of which are tributaries to the Caney Fork River system, which ultimately flows into the Cumberland River. If you were to map these out, all of these basilarii populations are shown right here on these different river systems that are numbered right there in that green polygon. So that entire branch right here, all of these samples comes just from that green polygon. And those are the different sampling locations. What they found though, was that each one of these river systems has its own distinct lineage of fish. So genetically unique that we might as well call them a different species. Because while they are morphologically almost indistinguishable, genetically, they are so different, they are clearly identifiable as separate genetic species. When we apply a molecular clock, right, that's the dating technique that's used to kind of differentiate how far back in time a set of genes had to separate from one another. And we can use that then to infer when 2 lineages separated from one another. Then what we see is we can actually put the divergence time analysis and compare it to the geologic record. Notice here on the bottom, here's the Pleistocene, Pliocene, and Miocene. So this one species, which everybody thinks is a single species morphologically, notice when it actually started to radiate or diversify. It started radiating and diversifying in the late Miocene, probably about 7-8 million years ago. What would have driven the diversification of a fish lineage into multiple lineages? What do you think? Downcut. And the evolution of different stream systems, right? Different tributary feeder streams. And the farther we go in time, the radiation continues, and we get more and more groups that are each associated with different river systems that flow across otherwise a relatively flat landscape, the Eastern Highland Rim. So, the final point on this, and we'll take a break, is that each one of these lineages is separated by an estimated 1.8 million to 8 million years of evolutionary history. That is our window of time. Now, put that up against the Ice Age. When did the Ice Age really begin? 2.5 million years ago or so. So it looks like while the weight of the ice might have played a factor in the early evolutionary history of this group of fishes, something else was already causing downcutting before there was ice. What was that something? It wasn't Africa colliding in. It was likely the impact of that mantle plume pushing up underneath the continent of North America before there was ice in North America. I don't want to get too complicated. I know those can, that's a lot I've just thrown at you. I'm just going to show you one last slide and then we're going to take a break. But a similar study recently has been done by Matt Niemiller, who's a herpetologist and is down at University of Alabama, Huntsville. He used the same kind of approach to study cave salamanders and arrived at some molecular clock divergence analysis dates as well. All right, we're going to talk now about what was the particularly the Pleistocene. That really ought to be sort of relabeled, that slide. What was the Pleistocene epoch like? Not necessarily the Quaternary period, but the Pleistocene epoch. Okay. Before we answer this question, one of the things I want you to think of is just imagine what, you would picture life in the Ice Age being like, Does it look something like what this picture captures? Or let me ask you another way. Are there anything surprising about looking at this image that seems to contradict what you might have imagined? Broadleaf trees, okay. Study it for just a few minutes. Like, look at that image real good. And do you notice anything that seems surprising? If so, just call it out. Those are camels back there. Yeah.
What are we supposed to be calling out?
Just looking for anything. This is sort of what I think of as like a stereotypical scene from the Ice Age.
Mm-hmm.
And is there anything that seems shocking to you or it's unexpected?
The stunted tree growth.
Okay, stunted tree growth. Someone mentioned also camels. There's no ice, says Kian. Okay. Yeah, that's a ground sloth, that dinosaur-looking creature back there is, okay? Very boggy looking, okay? So obviously it's hard to capture the Ice Age in one picture. This picture, while it's one artist's rendering of what maybe somewhere in, Ohio looked like, it doesn't probably do justice to what the Ice Age would have represented here in Clarksville, Tennessee. And we're going to talk about the biases that exist in being able to reconstruct what the Pleistocene was like. And some of those biases should be obvious to you. And I'll point those out in a minute. Let's keep in mind one clear fact, and that is that our ability to infer what happened deep into the Pleistocene is really limited, in some cases non-existent. Why is that? Why is it that the farther back we go, the harder it is to know what happened? Yeah. Right. The repeated covering of glaciers and glaciated environments especially has limited our ability to know what the region was like because everything's been bulldozed. Now, that's not true in Tennessee, but what is true here in Tennessee is a lot of time has gone by and a lot of land has eroded, right? We just gave you some great examples of river floodplains probably evolving and eroding 700,000 to 800,000 years ago. That terrace formed So whatever was there 1.2 million years ago or 1.5 million years ago, unless it was in a depositional environment that is still here, it's probably eroded away, or it never fossilized to begin with, right? So what would you expect before we go into this? What are some biases that we're going to probably be met with? One, we're only looking at the most recent from the Ice Age, mostly. What are some other biases? Because we're using fossils to reconstruct what the Ice Age was like. What are some biases around the kinds of fossils you would expect? Yeah, we're going to have a rich array of fossils that live in bogs and wetlands, but almost nothing from grasslands and upland forest and tundra. It's all missing. Woodlands, it's all missing. So 99% of what was here, we won't know because the fossil record didn't capture it, right? Okay, let's keep going. First of all, a very basic word about the Pleistocene climate. Now, I really will strive to do better in future classes to summarize what the climate of the Pleistocene was like based on more recent and relevant literature. This is a 1999 publication, which is quite old now, right? But the reason I don't have more recent records is there's still a lot of debate about what the Pleistocene climate was actually like. A lot of the standard papers, which were written in the 60s and the 70s and the 80s and maybe the 90s, they were written using approaches, which I'm going to tell you about in a minute, which are now somewhat antiquated and outdated. And there's good reason to suspect we may not be able to trust a lot of that science. So the assumptions made during the latter half of the 20th century may or may not be accurate. There's a lot of need for more information here. This is a very big area of needed research, by the way. So in terms of climate, you need to just be aware of that. There's not a lot of consensus. Maybe that's changed in recent years. I'll do better about incorporating that in the next time. Looking at Graham, 1999, he says the temperature south of the immediate glacial front, like on the leading edge of the glaciers, was about 6 to 8 degrees Celsius cooler than today at present. So right there in southernmost Illinois, temperatures were 6 to 8 degrees Celsius cooler than at present. That doesn't seem very cold, to be honest with you. So it's one surprise is it's not like it was 30 degrees, colder, or again, this is Celsius, so keep that in mind, but it's not like it was 15 degrees Celsius colder. Areas near the ice sheets experienced colder and drier conditions. That's an important component. Not only was it colder during the Ice Age, but we think it was drier. So cold and dry, that means there was probably more dust. And if it was drier, it could have also meant more wildfire. Anybody been watching the weather these past few days to see what's happening in the United States? What's happening, Jared? Massive wildfire covering something like 800,000 acres. It's crazy. That's happening in the month of February. So a relatively cold month, even for North Texas. There's probably a warm spell. But this is our most popular season. January, February, early March is like the most popular season for wildland fire, prescribed fire here in the Middle South. Because of how dry it is, it's a great time period to burn. But I suspect in the Pleistocene, it would have also been a good time to burn. So under drier with more mega droughts and long-term droughts, you probably could expect more in the way of fire. Precipitation dropped by as much as 30%. So 50 inches of rainfall is what we have today here. But back then, it was more like 35 inches of rainfall. That's probably comparable to easternmost Oklahoma today, or parts of northeast Texas. Some data suggests that cooler and wetter was the norm in the southeast, especially north of about 33 degrees latitude. And by the way, that is the line of latitude. That's probably about where Birmingham, Alabama is located. Whereas south of Birmingham, it was drier than it is today. Again, this is still stuff I need to probably be better about summarizing. So one of the ways, as we talked about during the Miocene, Pliocene, that we understand past landscapes is through the fossil record. And the best evidence that we have for the Ice Age comes from the pollen profile. And we talked about palynology being the study of pollen grains. Paleopalynology is the study of fossil pollen grains. And all plants are going to either produce pollen or spores. Many of these are going to be produced as what we call pollen rain. You know, usually about March, actually about this time of year, it's going to start soon. You're going to go out to your car and you're going to just have washed your car. Ken's going to have washed his pretty white Jeep out there. And he's going to come out and he's going to park under a tree and he's going to like, damn it, there's yellow pollen, sticky pollen all over his brand new washed Jeep, right? Well, that's pollen rain. That rain, that pollen is raining down almost like dust. And some of that is going to settle onto the surfaces of ponds and lakes and rivers. And some of that's going to then eventually settle to the bottom of the pond where they're going to be poor oxygen poor environments. It's not going to decompose very well. It's going to get incorporated into the sediment layers at the bottom of the pond. But those pollen walls are very durable thanks to a special type of polymer called sporopollenin, which enables them to be very long-lasting and very durable. It enables them to avoid drying out, for example, by the drying winds. So we can recover these pollen deposits in the sediments of ponds, and using a lot of complex chemical and analytical lab approaches, we can then analyze these. Now, pollen is rarely species specific. So you really can't use it like you could other, features to identify something to species, but you could get into a group of species or certainly to a genus, in some cases to a family. So like here's chestnut pollen from chestnut trees. You can identify things to the what we call the subfamily level pretty easily using pollen alone. You can then, for certain groups of oaks down here, you can differentiate whether a pollen is from one group of oaks, let's say the white oaks, or are they from the red oak group? You could differentiate that based on pollen alone. So these don't allow you to get down to full species, but they at least tell you some useful information about the ecology of that group. Others, though, particularly spores of things like ferns and relatives of ferns, this is a little group of plants called the quillworts, and they actually happen to be easily identifiable at the species level based on their spores. And you can see how small these are. This measurement here indicates 100 micrometers to show you how small these are. But these are two similar species, Isoetes texana and Isoetes flaccida, both from parts of the southeast. They're readily differentiated based on their spore characters alone. So put all that together, and then imagine that you're looking for some other things like the remnants of pine needles, maybe sections of wood, old pine cones, acorn caps. All these things can wind up in the bottom of ponds along with animal fossils, maybe the femur of a mastodon or the lower leg bone of a horse, right? Or a tooth of a bison. All these things can then build up to add to form a picture of what life was like. But what else can we add? What other kinds of factors could we add? We could look at what was the sedimentation rate in that pond. That tells you something about like how quickly were the soils building up, forming layers. That tells you about how much adjacent soil erosion was taking place. It tells you about whether or not the landscape was actively eroding or was it quite stable. How much charcoal is in there? That tells you about how much wildfire is burning on the landscape. All kinds of cool evidence. I'll come back and touch on some of that in a minute because that's a really important point we'll dig in on. This is what it looks like to be a paleopalynologist. This is my good friend, Matthew Valente in the bottom right. By the way, he is in your book. He is shown when he was a high school kid growing up in Alabama. He was good friends with Dr. Jim Lacefield, who wrote your book. This is he later on as a PhD student at the University of Tennessee, where he did a doctoral dissertation studying pollen of a valley in northeast Mexico. Now, this is what his research professor, Dr. Sally Horn, who was on my PhD committee, this is she and one of her students. They're sampling a bog. And so they use this, this core system to obtain a long sediment core. Then they take that back and they date all that stuff. They could tell, you know, how deep it was and what the age is. They use carbon dating primarily to be able to do that. Most of these sediment cores cannot go back farther than 35 to 40,000 years. So carbon dating is an appropriate way to age that, since carbon dating is accurate back to about 50,000 years. There are very few cases where it can go back older, meaning pollen core samples can be taken. In Florida, around Lake Okeechobee, they actually have some cores going back 75,000 years. But here in Tennessee, the oldest you can go back is around 35,000 tops. So that's one of the reasons why we don't know a lot about the early ice age. It's not in this region, it's not because glaciers covered stuff. It's that these ponds are not much older than 35,000 years at the most. If anything is older than 35,000 years, it's either filled up and become an upland, or it's eroded away or something. We just don't have sites that are that old. So once you take it back to the lab and you sample from various places and you date those different layers, then you go through this long period of process of extracting all the spores and pollen and pine needles and other things. We call those larger fossils like pine needles and cones macrofossils. And then these are called microfossils, the pollens and spores. It's just another image here. They can actually do it out on lakes. Dr. Sally Horn there, sitting there chilling while her team of students does the hard work. And then this is a site called Goshen Springs, which is in South Alabama near the town of Troy, Alabama. And this is a popular site that has been studied many times. In the boggy layers of this place called 40-acre pond, as they've taken those sediment cores down, one of the pollen grains that they brought back looks like this right here on the lower left. And it's been identified as belonging to a spruce tree. Well, spruce trees are northern species. As a group, they grow in the places like Canada. If we look at the nearest species of living spruce that's native to the eastern United States, we see red spruce comes down as far as the Blue Ridge Mountains in western North Carolina. But take a look at that yellow dot right there. That shows you where Pike County, Alabama is located. Yeah, come on, Iman. That shows you where Pike County, Alabama is. So they recovered spruce pollen from, 18,000-year-old sediments, but yet it's 250 miles from the nearest spruce population. So what's the inference there? If you got spruce pollen in Goshen Springs at Pike County, Alabama, at one point, not only is it colder, but spruce trees were there, right? Because obviously that's the way that pollen gets there. Now, we don't want to just look at one species. We want to look at the entire pollen flora, right? We also want to look for other things like gastropods and snails and, all kinds of other things that fossilize to be able to tell us what the paleoecology was like at this particular region. Let's take another look here. So in some of these sites, we actually have cones of an extinct spruce tree called Picea critchfieldii. These are 20,000-year-old spruce cones that are still in the sediments of those ponds, even though there's not a spruce tree now within 200 or 300 miles. That's pretty cool, right? And by the way, these are only usually down about 1 meter underneath the soil. So we're not talking about 3, 4, 5 meters. We're talking at a fairly shallow depth. So let's talk about some of the challenges with paleopalynology. Number one, we've already alluded to, they're really biased towards ponds and bogs and those kinds of habitats. So The dry habitats basically don't really get captured very effectively. There's also a possible tendency to overemphasize the importance of some groups. Think about things that drop a lot of pollen, like oak trees, for example. They may produce more pollen, but does that mean they were, and that pollen is wind dispersed, right? But does that mean they were actually more physically abundant at that site? Or is it just that they have the swamping effect because of the sheer massive volume of how much pollen they had? Versus what if there was some obscure type of grass that produces much less pollen that's 2 feet off the ground? Does that mean that grass wasn't abundant? So there's all those kinds of things you have to be aware of. One last thing is that the terminology of ecosystems has changed a lot. From the studies done in the 60s and 70s, people use the term forest very loosely. So they would say, oh, it's a forest if it's got 1 tree per acre, if it's got 50 trees per acre. We need more precision in our language than that. A forest is, in my way of using it, is a closed system that has a lot of tree cover, a lot of leaf cover, generally not grassy, it's shady, it's protected, it's moist, it's got shrubs underneath it. Then you got a woodland, then you got things like savannas, but all of which have trees, but they function very differently. Here's the warning. If you read the historical literature from the 60s and 70s, they say, oh, Middle Tennessee was a forested landscape during the Pleistocene. Well, I'm sorry, was it a true forest? Was it a woodland? Was it a savanna? Was it a prairie with 1 or 2 trees, right? These are all very different. They're very different ecologically, and they support different assemblages of plants and animals. A savanna will support many of different species than a woodland. Even though savanna will have 10 to 30% tree cover and a woodland has 30 to 50% tree cover, that's a lot of difference. Enough to mean that they largely will have many species that they do not share in common. So it's important that we are very precise. And what I'm going to teach you about in the last half of this class is how to make sure we are very precise with our language of ecosystems, and how we can sort of go back and look at older literature and understand what did they mean when they said this area was forested, because that's too broad of a term that we can't just sort of be content with just that one term alone. Okay. Now, we have a lot of pollen data. If you look across the United States, this shows areas where we have a study of fossil pollen sites here on the right, for example. All those dots on the right show places where they've analyzed for fossil pollen. That's a lot of places. That's a lot of data that we have on ecosystems from the pollen record. If we zoom in just over the southeast, these all show the sites that have been commonly surveyed throughout the past, say, 50 years. And if we zoom in over Tennessee, we can see many of these sites even still. Notice that here in Tennessee, we have, 3 or 4 different places that have been popular to study. One of the most important places in all of eastern United States comes from a place called Anderson Pond, which is located about 70 miles east of Nashville in White County near Sparta, Tennessee. And we have some very important sites also near Memphis on the floodplain of Nonconnah Creek. Those are really, really important sites. We're going to talk about Anderson Pond here a little bit more in depth. Now, 2 researchers, I barely missed these guys. When I was a PhD student at the University of Tennessee, Dr. Paul and Hazel Delcourt were still active professors. And I was gearing up in my very first, I was in my first semester getting ready to register for classes for my first spring in the spring of 2004. And I thought, man, I cannot wait. I'm going to take Dr. Delcourt and Delcourt. I'm going to take their Quaternary paleoecology course, right? These are the best of the best. I mean, these are leading experts worldwide. They've written numerous books. And damn it, they retired at the end of the semester. They literally fled to Canada and just got out of academia entirely. But Paul and Hazel Delcourt have this rich legacy, and their work is deeply respected. Now, some people have suggested, well, one of the reasons why they fled is that their work was starting to be overturned. I don't have any evidence of that. I don't know that to be true entirely. But I do know that recently people have suggested that some of their theories were oversimplified. Some of the things that they said probably don't hold up to really rigorous scientific scrutiny. And maybe they overreached in some places. Maybe their data didn't actually support that. Now, if we were to go back and reanalyze it, think about it. No, I don't mean to imply. I mean, they basically just gave up being professors a few years too early, right? A few years earlier than expected. And I honestly do not know the reasons why. But that's what people said. They said, well, we think they probably just, they were getting some pushback or blowback on some of their theories. I honestly don't know, and I probably shouldn't have said that. But what I will say is that, whatever conclusions they drew in the 70s and the 80s were done so with techniques at the time that was the best they had, right? They were at the top of their game, radiometric dating. It was the best that they had available. But those are different today. We have advances in carbon dating, advances in luminescence dating, right? And all these other approaches. So it's easy to look back now and Monday morning quarterback it and say, we can do it better now, or wait a minute, you guys were flawed in your approach. But at the time, they were pioneers. They were revolutionary, and they advanced the field of paleoecology in massively important ways. I definitely do not mean to diminish their contributions. So this is from a publication by Hazel Delcourt, 1979, where, by the way, Hazel Delcourt studied several of these sites like Mingo Pond in Franklin County and Anderson Pond in White County. And she studied many sites across the region, as did her husband, Paul. And from this, then, they could build this massive database of where all these species were at various points in time, going back from the present to 35,000 years ago. Remember, that's the farthest back we could go. Now, some of the recent work, and I'm just going to highlight this study here by Liu et al. From 2012, I believe it is. I think it dates to 2012, even though it says 2017 is when it's published online. I think it's a 2012 article. One of the things that Liu et al. Contends, and Liu, by the way, is a renowned palynologist, prolific publisher. One of the things that Liu says basically is that at Anderson Pond and in another pond up in Kentucky called Jackson Pond, which, by the way, is right up there near Elizabethtown, Kentucky, Liu et al. Contends that we cannot know what the vegetation was like at time periods younger than 13,700 years for Anderson Pond and younger than 15,400 years for Jackson Pond. Now think about that for a second. What the Delcourts, and I'm going to come back to this here, what the Delcourts had suggested was they went in and compiled pollen records for dozens of species. This is the Anderson Pond pollen record. And they compiled this record, let's say for pine trees right here, right? Starting at the present, going back in time all the way to 20,000 years. Notice here that pine is very minimal, and then it explodes in abundance at about 12,500 years ago. Pine really increases in abundance. That spruce trees, the genus Picea, is almost absent until 5,000 years ago. It begins to pick up, and then it spikes at the same time period. Quercus or oak trees are really abundant in the modern day, and they begin to slack off once we get back into the Ice Age. Remember, the Ice Age boundary is 11,700 years ago, right there. Look at the changeover here, here, boom, boom. That changeover that happens across many groups at the Ice Age, Pleistocene, Holocene boundary. They went on to do this for a lot of species. Here's a bunch of herbs and grasses and sedges and a few other shrubs. So they analyze, a few dozen species with these patterns. But Lou et al. Says, not so fast. They say, we cannot be confident of anything younger at Anderson Pond than 13,700 years. Which means that all of the Holocene and the latest couple thousand years of the Pleistocene, in their words, are unreliable. What would make the sediments that are younger than 13,000 years unreliable across all of Anderson Pond and younger than 15,000 years at Jackson Pond? What would make those sediments unreliable? Why can we not use those for inferring the scientific information of that site? What kind of factors might mess it up? Mess up the upper soil layers.
Animals walking through it.
Okay, so I'm hearing Jacob saying one thing, maybe water is moving pollen around, right? Maybe water is helping the pollen in the upper profiles to go down into lower profiles, creating mixing. Okay. Laura says maybe there's animals walking through it. Maybe there's cows. Maybe there's muskox or bison, right? Wallowing and walking and trudging through it. What are some other factors? Okay, so maybe, and keep in mind, this is already deposited pollen that's in this particular plot. What would cause the pollen in this particular soil profile to be unreliable? I think
The glaciers are going back, does that mean the uplifting and stuff, so maybe water isn't cutting down as much as it was?
maybe so. I mean, some of these sites might have still been cutting down a little bit because the glaciers were still depressing down the northern part of the continent. The biggest thing, and I think we're dancing on it, is bioturbation, right? The mixing of soils and sediments. Remember we talked about that term when we covered soils. You know, moles distributing those sediments around, earthworms, mammoths and mastodons and bison, or the freezing and thawing effect of the soil contracting. Remember in vertisol type soils, which these are not, soil can move and sort of shift. All those things mean that in the top layers of the soil, let's take a look at soil depth here. In the top 2 meters of soil, right, that's where all this disturbance has happened. It has mixed up those soils so much that it's mixed up the pollen grain so much that whatever inferences the Delcourts felt comfortable drawing in 1979, Lou et al. In 2013, reanalyzing those sites completely independently, says, we don't trust it. We can't even believe anything that's younger than 13,700 years. So that's important because I'll tell you why. The Delcourts use this model across many different sites to build a model of what the landscape of Eastern North America would have historically been like. And this is that model. I skipped a couple of slides and I'll go back and touch on some of those. But the Delcourts are famous among paleoecologists for coming up with this particular map. And what it shows is the glaciers, and this black band is tundra. Notice that the tundra band would have extended down. Here's where Indiana comes down. This is the Ohio River. That's the Wabash River. Carbondale, Illinois is right here. Clarksville's about right there. We're only 150 miles south of the tundra zone, according to this map. But think about what's here today, right? We don't have any tundra in northern Kentucky. We don't have any spruce fir forests across Tennessee, Kentucky, northern Alabama, Mississippi. It's mostly hardwood forest, right? Then down here, we've got oak, hickory, and southern pine trees, according to the Delcourts in the Ice Age. But today, that's largely a region of pine savannas. So the general premise is this, that whatever we have today was greatly shifted southward during the Ice Age as the temperatures plunged And as the glaciers advanced, the tundra was moving slowly ahead of the glacial front. The taiga, the boreal forest, was moving ahead of it. And so normally that boreal forest would be up here, right? It greatly shifted to the south. The deciduous forest common today from southeastern Minnesota to Maine to northern Florida and Texas, notice where they were shifted to. They were shifted into this zone. The richest forest of like Great Smoky Mountains National Park or Fall Creek Falls State Park, those really rich, what we call mesophytic forests, these deciduous hardwood forests that are really super rich, were forced into these very protected zones along rivers, like along the lower Mississippi, the Alabama River bluffs of Alabama, the Savannah River here. This is the model of the Delcourts. Now they also purported or proposed some other, now I think pretty radical and unrealistic and overly simplified concepts. For example, they said that a lot of the species that were here that did not live in forests, that let's say lived in grasslands or lived on a particular rock outcrop type, both plants and animals, they said, no, man, conditions here were just too harsh for them. So in order for them to survive this close to the glacial front, they had to migrate. Well, many of these species have, like that little Cumberland rosemary bush I told you, they have almost no ability to migrate quickly. They don't have no known animal carries their seeds for them. Their seeds don't get carried by wind. They don't get carried by water. That's the case of hundreds of species. They are poor dispersers. There's no really good mechanism to say explain how they might travel hundreds of miles in a few thousand years. So we then have to think about models for where those species might just stay put during glacial times. Maybe they don't migrate. Maybe they stay put while the conditions around them do get colder and they're surrounded by boreal forest. Anyways, long story short is a lot of vegetation types shifted. And then when the glaciers retreated, what do? They rebounded and moved back to the north. A big part of the second half of this class will be picking up on that topic and sort of understanding and disassembling some of that. Because I do very much believe that's a gross oversimplification of what actually happened. So I want you to know this. I want you to study the Delcourt map. This is a big part for sure I'm going to ask you about on your midterm exam. And we will touch on this frequently, but I want you to also generally accept this very loosely and sort of don't put too much stock in it, okay? Okay. Now, because things were shifting so wickedly back with, dramatically different climates, a lot of species were coming into contact with each other that we wouldn't think of being together, associated together today. Spruce trees were growing in a bog in South Alabama next to pitcher plants. A longleaf pine might be growing next to a fir tree. There's no place today where you can go to see that. So what we say is that the conditions during the Ice Age have no modern analogs. There's not any place really you can go to see equivalent vegetation, equivalent landscapes in the Southeast to what kinds of vegetation would have existed here 15, 18, or 25,000 years ago. Here's a good way to visualize this. This is some vegetation models from the 90s that show sort of the change in all these ecosystems, prairies, different forest types, woodland types, tundra, over a period going from 18,000, 12,000, 3,000, all the way to the modern period. And you can see how those vegetation types are modeled and suggested to have shifted through the course of time. These areas in red indicating regions with no modern analog equivalents. Now, it's clear there were areas that today resemble the Ice Age, right? If you go to Upper Peninsula, Michigan, it looks a lot like probably Ice Age conditions of spruce forest here in central Tennessee, probably would look like modern day Upper Peninsula, Michigan. You go to a bog in Vermont, probably looks very much like a bog you would have seen in Ice Age Pennsylvania, right? There are areas with modern equivalents for sure. Any questions about that? Let me hit you with a real cool example. So I think we've hit pollen and its utility for inferring vegetation during various epochs of the Neogene and Paleogene. Let's take a look at one of my very favorite things to talk about in this class. So there are two other specific examples where we can use animals and the things they collect to help piece together the paleoecology of a given region. So take this Arctic ground squirrel, for example, that lives up in northern Canada and Alaska. It goes around the tundra harvesting moss and juniper needles off of little shrubs and parts of mushrooms, bones of dead rodents. It confiscates, right? And it brings it back, and underneath the ice or underneath the frozen permafrost of the tundra, it builds a nest, or what we call a midden. And this is a fossil Arctic ground squirrel midden from the Ice Age, from northern Canada. And so now researchers can go into that. They can sample it, they can date that, and then they can reconstruct what vegetation would have been like at the time this nest was constructed. That's cool. But now look at here. This is my favorite example. This is the desert Southwest. So this would be like Utah, somewhere like that. And there are pack rats that live up around these canyons and the bases of these sandstone cliff lines. The genus is Neotoma. And so we have some pack rats, a couple species of pack rats in this region. And pack rats have the pesky little habit of confiscating and harvesting things. Check out this quote from 1849 from the California Gold Rush. It says, "Partway up, we came to a high cliff, and in its face were niches. And in some of them, we found balls of a glistening substance looking like pieces of a variegated candy. It was evidently food of some sort, and we found it sweet but sickish. And those of us who were hungry, making a good meal of it, were a little troubled later with nausea afterwards." What they were eating was the nest of a pack rat, where the pack rat had pooped and peed over this nest, not just once or twice, but for thousands of years. And so this pack rat's been, this whole family, lineages, generations of pack rats have been inhabiting this single cliff face for thousands of years. And every time they go out and get a metatarsal bone of some deer, and they get an antler of something, and they get some needles and pine cones, they just come back and nibble on it and poop and pee. And in that arid Southwest climate, it just gelatinizes and hardens so that when the Gold Rush guys were coming by and they were all hungry, they thought they found somebody's candy. That's pretty cool. How you like that, Molly? Isn't that great? Hey, but Molly. I know.
Thank you for validating what I said all my.
But the question, Molly, is how old can these be? All right. Well, here they have confiscated the metatarsal of an extinct mountain goat, the pines, the needles of the limber pine, which no longer grows around this location. And this particular midden from which this image is taken is 27,000 years old. But that's not the oldest. Here's one that is 51,000 years old, located in the Southwest, and it's a massive midden. So we can tell a lot about vegetation change in the desert Southwest using these approaches. And we can map these. And so you can see these are all the midden locations in the Southwest. And that's a lot of valuable biological, ecological data that we can draw from to look at reconstructing past climates and vegetations, animal assemblages dating back 50,000 years. Okay, let's switch gears real quick. Actually, it's time for, no, I want to cover one more topic, one more slide, and then we're going to take a break. So about 2 more minutes. Now, with animals, we've been talking about plants. How do we get animal assemblage data? Well, just generally speaking, we can get lucky. We can find caves with Pleistocene. Thank you, Molly. We can find caves with Pleistocene animal remains. This is a cave in North Alabama where there's some fossilized remains of saber-toothed cat. Pretty cool. And this shows a team of paleontologists doing a dig. This is about an hour west of Huntsville, Alabama. Sometimes paleontologists, by the way, these are the images from your book, right? That great book you got is full of good information. I hope you're reading it. Here they are breaking their backs as they find Ice Age horse teeth and the cheek tooth of a beaver. All of these are probably from the Ice Age. During the pandemic, when my family and I lived in Clarksville, we moved away from Clarksville in March as soon as the pandemic began to hit. We moved south into Dixon County. And that summer it was a weird summer, right, for everybody, because we're like, oh, man, what do you do? What do we do with our time? I mean, I found myself being on the clock, but yet I was like at the creek every day, you know, taking a business call while I'm swimming in a creek, thinking, God, I should be at work, but yet I'm having family time. It's great. So one day, my family and I go to what's called Turnbull Creek, and out in Cheatham County or Dixon County, and we're swimming in Turnbull Creek, and my wife walks over and she's like, "Hey, what is this?" And she had found an Ice Age horse tooth. I wish I could find that because we've put that away somewhere. I don't know where it is. But anyways, this is the way a lot of good fossils are first found, are by treasure hunters and teenagers and people who are just checking their property, and they find things and then they ask questions, and maybe they contact a specialist, or they contact a local museum. They come out, and then it leads to even cooler discoveries, like maybe an entire skeleton. When I was a first-year professor here, I went out with one of my students to West Tennessee, was walking in a creek very much like this, and I discovered the vertebrae of a mosasaur, one of those sort of swimming reptiles from the late Cretaceous. And then you have sites like this where was actually in the corner of someone's yard. Y'all know where Cool Springs Mall is in Franklin or in Brentwood, Tennessee? This is like a real popular shopping place. And this is what it looked like back in the 90s. It was mostly a rural landscape. About a mile from Cool Springs Mall is a neighborhood adjacent to a golf course. And in the back corner was a ditch next to someone's house. Person goes out, the homeowner's out there just kind of mucking around in the ditch. And they discovered massive bones sticking out of the side of the ditch face. It turns out that those were the bones of a mastodon, an extinct elephant. And they also found then what they perceived to be spear points co-located beside these mammoth bones. For a long time, we thought that archaeologists and paleontologists thought that that was a mammoth kill site or a mastodon kill site. It now is one of the most famous late Ice Age fossil sites. It's called the Coates-Hines-Litchie site, and it has yielded a wealth of information about Pleistocene horses, beavers. There was a beaver pond there historically. No site of beaver or a wetland even there today. And it has some of the best mastodon remains around. All right, with that, we're going to take a break. We're going to come back at 6:53, and we're going to do a quick tour visually to look at the animals of the Pleistocene.
I was just telling somebody it's like you condensed down 20 courses I took in college and added another 5 I wish I'd taken and condensed it all down into one class.
Well, how do you know it's even accurate? Because I've never had any of these classes.
Well, as long as you convince everybody.
Okay, so now let's shift gears. This is actually one of, I think, probably the most exciting sections. It's gonna be a fast section. We're just really gonna just hit the highlights on some of the cool animals that lived at all the way up until the very end of the Pleistocene. It's an amazing array of animals that rivals anything you can imagine from Africa or Asia in terms of big animals. This is a somewhat grainy and small scale version of many of those animals, but just take a look at some of these groups, right? Not just one, but multiple species of what we call proboscideans or elephants. Look at all the horse diversity, including zebras. Lots of camel diversity. We had multiple kinds of beavers, capybaras, lots of pigs and peccaries, mountain goats, sheep, musk oxen of at least 2 to 3 species, 3 to 4 species of bison, lots of different kinds of deer, caribou, reindeer, moose here in the south. Many different types of canines, from dire wolves to hyenas. Crazy stuff. Lots of cats, all the way from your typical species like lynx and bobcat, mountain lions. But then this amazing array of things like scimitar cat and saber-toothed cat, jaguar, lions, cheetahs, all here in this region. And a big whole host of different bear species like short-faced bear, cave bear, polar bear, black bear, brown bears, all that kind of stuff. Now, not every one of these live in Tennessee, but many of these, and not all these live in the southeast. And this isn't even all of them. I mean, there are other things that aren't even represented on this diagram, like pronghorn antelopes. I don't see those on there at all, which are missing. So anyways, let's get to it and just sort of go through in a little bit more detail some of these cool animals. As I mentioned, there were multiple elephants. The most common one for us here in this region was the smallest, called Mammut americanum, the American mastodon. This was a hairy, sort of smaller species, but it's still, around probably 1.5 times larger than the modern day African elephants. I mean, these were big. Tusks of these have been found in the Harpeth River. There's when we go to the Tennessee State Museum, you'll see a tusk of the American mastodon. The woolly mammoth, Mammuthus primigenius, was more of a species of the really cold regions to the north. That shaggy coat. We didn't have those particularly in this region. But the largest one is the Columbian mammoth, which you see is dramatically large there on the far left. We did have records of those here in the east. Places like Saltville, Virginia, which is just over the line from northeast Tennessee, but all the way down into Florida. They would have likely been here in Tennessee too, although we don't have a lot of records of true mammoths here. This is the foot of American mastodon, so very large. And that's the molar of a mammoth that you see from Alabama right there. Lots of bison species. The oldest one we had is called Bison latifrons, shown on the far left. It basically looked like a very large Texas longhorn cow of a bison. Then we had Bison antiquus, which is a western species primarily. And then Bison antiquus, shown here, hybridized with Bison occidentalis, which is another sort of western species. Those two gave rise to the modern day American bison, which is the species called bison. And we'll come to talk about, when we get into the Holocene, about how older bison records from this region, like from the Pleistocene, are mostly either Bison latifrons or Bison antiquus. The young bison records from the last 500 years are bison. And we'll talk more about that later. Here's an artist rendering showing saber-toothed cats attacking bison. And this was a common migration point for numerous species of bison. And this is the falls of the Ohio River James and I were talking about up in Louisville, Kentucky. Bison would use this as a crossing point to get across the large Ohio River. Daniel Boone, when he explored the falls of the Ohio in 1774, remarked about how there was fossilized bison dung stuck to the rocks even at that time. Now, he used the word petrified. Does that mean it, it's truly petrified from days of old, or was it just hard dung that had been there for a few years? In any case, this was a major bison crossing point. This is a woman from your book showing a Bice-age shoulder bone from the stream in the Black Belt of Alabama. Bison teeth from another stream. We had numerous species of horses. That Coates Hines Litchie site from near Cool Springs Mall also had ancient horses. Many different species of horses, some of which were zebra-like. Some sort of resemble Przolowski's horse of Russia and Mongolia. Again, fossilized horse teeth shown here. Multiple species of camel, paleo llama, Hemialchinia. I think I'm pronouncing that correct. Some of these were similar to like the Bactrian and dromedarian camels. Some were similar more to alpacas and llamas.
I got a question.
Yeah, what's up?
How, how can you, how can you tell from the fossil record if a horse had stripes?
That's a great question. I don't think you can.
Okay,
I think there's yeah, they probably would have to, zebras anatomically and morphologically probably have more, and I'm saying this as not being a mammologist, but I'm assuming the zebra line of equines or the horse family probably have certain signatures that other horse groups do not have, right?
I see. Okay,
It sort of is like in similar ways how, anthropologists can study, not fossilized remains, but they can study remains of, different groups of people and tell whether they have Mongoloid features for East Asian, or if they have Native American features or African American
you.
features through various parts of the skulls and other kinds of parts of the human anatomy.
I got you. Thank you very much. That helps.
There's a lot of artistic license that is taken with sort of these artist reconstruction, these renderings. These are all teeth of Paleo llama from the Ice Age here. And let's also not forget that from the tooth data alone, not only can you tell that, yes, this was a llama, if you're trained in mammal teeth, right? The wear patterns can tell you about what kind of plants they were eating. Were they browsing on forbs, which are wildflowers and shrubs and tree saplings, or were they grazing on grasses? Well, the dentition patterns, whether or not you have flat grinding molars like those mammoth teeth, for example, or whether you have very architecturally sort of, complex molars like we do. We're adapted toward a diet of eating not just grass. That's why our molars are kind of sculpted. Mastodons have sculpted molars, which indicate they were browsers. Mammoths have very flat molars, which indicate they were grazers. Then you can look at the tooth enamel and tell by isotope analysis whether they were eating primarily grasses or primarily forbs or shrubbery. So you could tell a lot about the paleoecology of a region simply by teeth and studying those teeth. We had musk oxen. Now, these aren't the type of musk ox you'd see in places like Alaska and Greenland today. This is called Harlan's musk ox, and this is a common fossil from just over the line in Southwest Virginia. We had these in Northeast Tennessee too. We had the elk moose, which is also known as the stag moose. We also did have true moose here in this region during the Ice Age. And by the way, this is one of the few species I'm going to show you which is no longer truly extinct. Of all these other ones I'm showing you, more than 36 genera of mammals are totally extinct now today. They went extinct at the end of the Ice Age. We had red deer, which today you see in Europe. We had caribou that ranged south into the mountains of East Tennessee, at least. We had two kinds of sloths, Eremotherium, very large giant sloths, and we had Megalonyx, and this was named for Thomas Jefferson. Thomas Jefferson was a fan of fossils, and he had received some early fossilized specimens of this, which became known as Jefferson's ground sloth way back in the 1700s, or early 1800s, I should say. Megalonyx jeffersonii. One of the places that we have in Tennessee called, and by the way, here's some fossils of that from Alabama. This is that cave I showed you in North Alabama. This is the same cave from which these fossils of the ground sloth came from. This particular fossil of the rib bones of a giant ground sloth has the tooth marks of a saber-toothed cat. And that same fossil site in Colbert County, Alabama, has the skull of the saber-toothed cat, Smilodon. It was found there. But a famous cave site in Tennessee over in Warren County called Big Bone Cave. This is the inside looking out. And this was a known site for Megalonyx jeffersonii, Jefferson's ground sloth. There's some fossils that have been found here. I think they're in the Smithsonian today. We had tapirs, multiple species, both long nose and flat-headed peccaries. We had pronghorn antelope, one species, maybe more. And based on the speed of the pronghorn and how fast it runs, it's North America's fastest land mammal. Well, if you look at various antelopes and stuff in Africa, they run extremely quickly because they are chased by a very fast predator, in this case, the African cheetah. So you might predict that if you have an extremely fast land mammal, herbivore, like a pronghorn, it might have had an extremely fast predator, in which case you would be right. We actually have our own American cheetah. Now, this artist rendering may or may not be accurate. We actually don't think it was very closely related to the African cheetah all. In fact, it was a close cousin to the modern day mountain lion, which is a cousin here in North America. This is probably what it looked like. It was larger, faster, slimmer body, but it would have raced across the grasslands. And by the way, there's an article here to a recent discovery, excuse me, of the American cheetah from a cave in Lee County, Virginia, which is that southwesternmost corner down where Cumberland Gap, Tennessee is. So they recently discovered a fossil of microionics, which is the American cheetah. This is the artist rendering showing what it might have looked like. And you can see some of the other big cats. That's it on the far left, microionics there, in contrast to Puma concolor, which is the modern day mountain lion shown here. They're all sort of in a general clade that is somewhat related to the African cheetah. But we had a range of big cats. In addition to mountain lions and American cheetah, we had jaguar, we had saber-toothed cat, we had the American scimitar cat, and believe it or not, the American lion was the largest lion species of all time. North American jaguar was something I've only recently become aware of. It was larger. This is Panthera onca augusta, which is larger than the South American or Central American jaguar. This is actually Jaguar Cave in Fentress County, Tennessee, up on the Cumberland. This is one of those caves, by the way, that they did those paleo sediment studies from. This exact site has both 15,000-year-old footprints of North American jaguar, which is extinct, and it has 4,500-year-old footprints of a mother and daughter, or a mother and child, walking in these muds of these caves. So really tremendous fossil sites. Look how large the footprints are of those jaguar tracks. This is an extremely sensitive site. It's obviously highly protected. The location is highly protected. This is another known jaguar cave. This is Salt River Cave in Jackson County, Alabama, which has a recent discovery of a jaguar full skeleton. And that shows saber-toothed cat, Smilodon fatalis. Most of us have grown up calling these saber-toothed tigers. They're not related to tigers at all. There were multiple members of the genus Smilodon. Smilodon populator was a South American type. And here's a Smilodon fossil, part of a jaguar tooth and a bobcat tooth. And all of those were from that same cave in Alabama. Scimitar cat, kind of similar. Big cats as well. I mean, dangerous place living in Pleistocene, North America. And then last summer, or maybe the summer before, when we had that big mega drought, it was one of those big droughts, not a mega drought. It dried up a lot of the Mississippi River. I think it was last summer. Large parts of the river had drawdown zones, and this guy was walking out just south of Memphis, found the lower jawbone here of an American lion mandible with the tooth. And here's a reconstruction of the American lion, Panthera leo atrox, nowadays just referred to as a full species, Panthera atrox. Big lion, the largest in the world. There's a full fossil skeleton of American lion. And believe it or not, we also had ocelot. And Theo sent me an image this morning that shows the type specimen of the American ocelot, which comes from, of all places, where do ocelots tend, where do we think that they live today? Where would you go to see an ocelot? South America, Central America, Mexico. They also are in southernmost Texas, like down around Brownsville, Texas. But in the early 1800s, in like 1818, the English explorer or Scottish explorer, which is it, Theo?
He was English.
Yeah, Thomas Nuttall discovered or reported ocelots. And in fact, he harvested a specimen, which ultimately now is on in storage or on display at the Museum of Natural History in Paris, France. That was the type specimen from which the species ocelot was originally described. So ocelots.
Yeah, he didn't collect it, but
Someone else did.
It's from around that time period, or even earlier, maybe.
Got you. Okay. So ocelots at one time, at least up until a couple centuries ago, were at the latitude we are now, more or less, in Arkansas. But during the Ice Age, we had ocelots here as well in Tennessee. And of course, we don't know what we've lost, right? I mean, there's been so much ecological change. We had short-faced bear. I mean, that looks absolutely ferocious. Chasing a little baby bison, poor bison. Dire wolves. We had things like martens, small mammals that are mostly thought of today in the boreal forest of Michigan and southern Canada. We had Glyptotherium, the giant armadillo. Giant beavers. Some of these were the size of a small black bear. And in comparison to a regular beaver there, we had two species of capybaras. This is an artist rendering of Holmes's capybara. We had things like Arctic shrews, which we don't have today, a variety of types of ground squirrels and all kinds of rodents, too numerous to name. But I give these here because these are known species that still exist today, mostly in northern latitudes like the snowshoe hare, which is found farther north and out in the Rockies. Okay, we did good. We got through that. Now what I want to do is switch out in the last part. And I want to talk about in these last 15 or 20 slides, Clayton's about to fall asleep on me, so I better get y'all to start doing some stretching over here. Everybody stand up if you can, just kind of stretch it out. I need you guys to be alive and awake this last 25 minutes or so here. Okay. Was that cool or what? Did you know about all those animals being in North America? Some of the most diverse megafauna on the planet was in North America. Now, let's talk about, let's bring it forward to a point in time of roughly 13 to 14,000 years ago. That's when a lot of those species went extinct. Now, they didn't all go extinct simultaneously like the dinosaurs did, right? The dinosaurs was a very abrupt extinction due to a major meteorite impact. In the case of all these mammals, many small, some large, many large, we don't really know the exact cause of their extinction or their decline. We're going to pursue some of that. So let's ask the basic question. What explains the disappearance of all these animals at the end of the Ice Age? It wasn't the exact end. It wasn't 11,700 years ago. Excuse me, it was 2,000 or 3,000 years before the end of the Ice Age. And for some, it was even a little bit before that. So they were kind of winking out or phasing out. And some of them even lasted longer. Like the last woolly mammoths existed on an island off the coast of northeast Russia up until about 3,000 or 4,000 years ago. So some things persisted while many of them did go extinct. First of all, let's set the scene of what the American landscape probably was like at that time. We're going to go to about 11,000 years ago. This is actually technically just inside the beginning of the Holocene by about 700 years. But for all intents and purposes, 2,000 or 3,000 years doesn't make a difference. Number one, the coastline is about where it is today. It's going to continue to rise because these glaciers are going to continue to retreat backwards, right? Notice how places like Miami, parts of southwesternmost Everglades are underwater at this point. So that coastline is going to change a bit. These glaciers will retreat at about another 1,000 miles to the north up to where they currently are. At the front of the glaciers, you've got proglacial lakes. Remember that? The ones that occur right there at the glacial front. Notice then you've got, really for the first time, your modern rivers, the Ohio, the lower Missouri, and the Mississippi. Now, those rivers have sort of been generally in those regions. But remember, things like the glaciers moved a lot of those rivers or displaced. But what do you notice about those rivers that seems to be really dramatic in this illustration? They're very wide, right? I mean, we're looking at an entire snapshot of the continent, and they are purposefully drawn as being probably many miles wide. And that's because those glaciers are melting rapidly, and they were many miles wide. They were creating outwash plains. Remember those northern Pleistocene Valley terrain deposits? That's when they were laid down. And there are boulders and cobblestones and tree trunks and sand blowouts all being carried downriver, a massive volume of fresh water entering the Gulf of Mexico. And that is also affecting the salinity of the ocean water. Now, call attention to this area up here in the northern Great Plains in southern Canada, where you've got a bunch of these glacial lakes that are developing. As those glaciers will continue to pull northward, eventually that barrier, which is the ice, won't be there anymore, which means that giant pool of water is going to be able to drain somewhere. And so that is going to affect the climatic stability at the very end of the ice age. That's one of the big things. As that fresh water spills off of the land, that's going to have a big effect. We're going to explore three factors. Factor number one, leading to the decline of these animals and the shift from the Pleistocene to the Holocene, is rapid environmental change. Okay. So I have purposely flipped this diagram, and I meant to relabel it so that everything wasn't backwards, but I wanted to do it because I like to look at it better from left to right. Okay. So what we have here essentially is, probably should have kept it the way it was. What is that, like 20,000 years? Yeah, 20,000 years ago in the Pleistocene. Here's 15,000 years ago. The temperatures here, which is what we're looking at on this axis, that's temperature. Notice the temperatures are low. And then we hit a spike right here. We hit a cool period followed by a warming spike that continues. Okay. So cold, warm spike, warm, cool fluctuations, very cold, almost like it was in glacial times, boom, warming rapidly, stays warm all the way to the modern day. What I want to do is explore this fluctuation of temperatures, because some people think that rapid change in temperature and climate over decades or hundreds of years is what probably was what was driving these species to extinction, or was one of the causal factors. So that initial, I've got these in reverse order. Yeah, I think I won't reverse these next time. Yeah, hell, I had that totally backwards, right? I think I did. I think I had it totally backwards. No, wait a minute. No, I'm good. We're good. Yeah. This is basically the dividing line between the Holocene here, the Pleistocene here, and everything from here on is the Holocene. So these events, this Bowling Allarod warming episode, and what's called the Younger Dryas cooling period, those are really significant events that kind of straddle that Pleistocene-Holocene boundary. Right? This is why I changed them, because I wanted it to kind of align with this, but I realized I probably just butchered it. So I've got some links here. I would like for you to, these are just Wikipedia links. I'd like for you to read up on the Younger Dryas and the Bowling Allarod if you want to. But I'm going to briefly just kind of hit the highlights on some of these. Again, there's that boundary between the Pleistocene and the Holocene right there. So let's break some of this down real quick. Number one, we've got here in terms of thousands of years before present, 100,000 years all the way to the present. What you can see is these fluctuations are tracking. Now, this is oxygen 18 isotope, which is a proxy for temperature, right? Just remember, oxygen 18 basically tracks temperature directly. So as the temperature is fluctuating at a very regular sort of periodicity through the ice ages, right? That is going through stadials and interstadials. Those are what those are. And what is kind of tracking that, or what's driving that, largely are things like the Milankovitch cycles, are kind of creating some of that that shift in orbit. And then when we get to the Holocene boundary right here, this is that very warm spike called the Bowling-Allerod warming period, followed by this dramatic cool-off, which we call the Younger Dryas. And the reason we call it the Younger Dryas is to differentiate it from the Older Dryas, which is this cool-off right here. And after that, we hit the Holocene warming period, which we are in today, with warm conditions. So the question that I want you to kind of think about is, what was causing this climatic instability that is what people think maybe was driving a lot of these animals to extinction? Because think of climate instability was changing vegetation types. It was changing food sources. That's one of the ideas, is that it was so much change so rapidly, it was leading to trophic cascade effects. Well, we don't know exactly the cause of climatic instability, but I'm going to kind of enlighten you on a few possibilities. Number one, as the glaciers were retreating here, you have this massive buildup of proglacial lakes with the Great Lakes and with Lake Agassiz and so forth. And eventually that buildup of fresh water burst through various outlets. A lot of it would have had massive outflows down the Mississippi, massive outflows through the St. Lawrence River, and massive outflows northward to the McKenzie River, until this glacier got to about right up in here. And then there was a massive outflow through the Hudson Bay into the North Atlantic. Putting all that fresh water into the global ocean would have infused a bunch of fresh water and would have affected the ability of the ocean to form sea ice, because more salt, the higher salt concentration, when you affect it with when you affect the salt concentration, it affects the freezing temperature of ocean water. And so if you upset that balance of salinity, it can drive it into less sea ice development or into more sea ice development. And what we're talking about here is more fresh water would have upset that balance in ways that probably would have led to less sea ice development. Less sea ice means less reflectivity, less cold, right? The more ice you have, the colder it is, the more light and heat is reflected back to the sun. So I encourage you to go back and watch that video on the Milankovitch cycles, just kind of rehash on that. I don't want you to know the details. I just want you to be exposed to some of the generalities here. Now, researchers have been discovering that with all this freshwater melting that's happening, the implication is that you've got these warm ocean currents and you've got these cold ocean currents, and that influx of very cold fresh water could have affected those ocean currents, and it could have affected the salinity, as I mentioned. That's part of what we call the thermohaline cycle, which basically governs the world's ocean current circulation. So if you have a huge influx of cold, fresh water, it doesn't just impact the North Atlantic. That water is carried elsewhere throughout the globe and can result in major climatic changes very quickly, right? Now, another thing you would expect with a lot of melting quickly is icebergs are calving, right? They're breaking off. And so what you can have then is an expectation, a prediction of a lot of icebergs floating into the North Atlantic. Many of those icebergs actually carry what's called ice rafted debris. So there are rocks and dirt and all kinds of stuff, logs, possibly, probably not because it's ice. Rocks and ice especially are caught up in these icebergs. Those then raft out into the ocean. And then when they melt, all that debris sinks to the bottom and then it can be studied, right? So underwater paleoarchaeologists or whatever can study these debris fields and say, this rock, this cluster of rock was brought here from northern Canada, but yet today, maybe it's off the coast of Ireland. those are very useful for understanding like the amount of fresh water and ice that was breaking off the glaciers of North America. I tell this to you not because I want you to know the details, but to just know all the branches of science that are how they're coming together to inform this very complicated topic. Like, think about that. Studying rocks that have been rafted out into the ocean that have somehow been dropped 10,000 feet to the ocean floor, that we can actually study those things and find out where that rock came from and use that to understand patterns of iceberg drift. It's incredible. So this rapid climatic change would have shifted vegetation types, as we've talked about earlier. Taiga would have dramatically shifted. Take a look between the map on the left, which is 13,000 years ago, and the map on the right at 11,000 years. So just 2,000 years separates these. Look at how taiga, the spruce fir boreal forest, would have shifted dramatically up, almost completely displacing in just 2,000 years. It moved completely up to this place. The cool temperate forest that was here dramatically expands and shifts up. The warm temperate forest dramatically expands and shifts up. So there were major vegetation shifts. Could the animals keep up with that degree of change? That's a lot of change, right? So animals were moving and migrating, trying to adapt to warming climates that was highly unstable and fluctuating. Now, one of the greatest pieces of evidence of this instability comes from places like Anderson Pond. Remember that site? So this is the site, and this is not the same diagram from Anderson Pond, but we have similar kinds of diagrams from there. This is a paper that's talking about Pleistocene megafauna collapse, novel plant communities like new plant communities, and enhanced fire regimes in North America. What this shows is, and just follow me for a little bit here, but it shows spruce pollen and pine pollen of a particular northern pine called jack pine. There's oak pollen. Let's look at those first. Spruce, which is really indicative of boreal forest, was really abundant from 16,000 all the way to about 11,500 years ago. Then it crashed. That's that Holocene boundary. Okay. Then things like oaks were not abundant at all until we get just a little bit at 13,000. But notice at about 11,000, they begin to spike. So it's a complete reversal of pattern. Northern species were being wiped out. Southern species were picking up at that boundary, right? This is all taking place, though, when megafauna were going extinct. And what else was happening? People were arriving for the first time. Now let's take a look at over here. These are the last two I wanted to focus on. This is called sporomyella. These are the fossil spores of animal dung fungus. So the fungus that lives on cow poop or bison poop forms a certain spore type that we can track. And notice how much fossil dung spores are evident all the way up to the end of the Ice Age, and then they almost vanish, right? That tells you there were a lot of big animals on the landscape. Then they crashed, and then there's a very low level. Now, those big animals are doing a lot of eating and grazing. They're eating down the grasses. Maybe they're eating them down real short around those ponds. What that means is the shorter the vegetation is, fire can't move easily. If you mow your yard religiously and a wildfire sets out, fire cannot rapidly move across a yard that is 2 inches tall, right? But this shows the inverse relationship between the animal dung spores and charcoal from fire. So notice how little fire is present in the Ice Age, although there are big spikes right here. And that's a very important spike that we're going to come back and talk about. The one at about 13,700 years is a big important spike. Notice, though, that it's sort of intermittent. Fire is definitely on the landscape. And fire is on the landscape probably before people got here, or at least at the time they were arriving. But as the megafauna disappeared at this point, fire really picks up. There's probably more fuel. There's more vegetation that's ungrazed, more vegetation to burn. That all makes sense? All right, I encourage you to take a look at that article. I wish I'd included a hyperlink to that. It was published in Science, 2009. Really great article. It talks a lot about this stuff. So let's go back and touch on this particular spike of fire right there. Some researchers started questioning, well, is climate change enough to really cause the decimation of 36 different genera of animals? Is that enough, right? We've had climate change episodes in the past where that many animals didn't go extinct. What was so special about this latest time? Well, in addition to having a spike of fire in many places around the world, as evidenced by soot deposits and charcoal deposits, there's also a lot of a type of element, I'm going to come back to this one, called platinum. Platinum is especially abundant in meteor impact sites, kind of like the element iridium we talked about with the dinosaur extinction. Researchers started finding evidence of large-scale wildfires connected to that time period of around 13,700 years ago, all across different places. Take a look at this. Younger Dryas boundary, biomass burning proxies plotted against impact-related proxies. And what they were seeing is sort of two things: a bunch of platinum element and a bunch of soot and wildfire signatures. Think about the effect of a massive meteor impacting the landscape. By the way, I've just got 2 slides left. We're gonna be done. We got 8 minutes. A massive meteor impacting the landscape, creating some of the biggest wildfire disasters that this continent has ever seen. This is an emerging theory that is gaining steam, or hypothesis that's gaining steam, and has lots of publications behind it. But there are also a lot of hotly debated arguments over it. There's a whole camp of scientists that say that's bullshit, we don't believe it. But then there's some very reputable scientists who are publishing and getting behind this. Time will tell. This is the nature of science, right? People thought that the guy who came up with the theory of continental drift was out of his mind. And eventually, you know, so did they think that about Charles Darwin. But these things have a way of working themselves out over time, one way or the other. So what's the evidence? Big spike in signatures of massive fires and platinum anomalies, these big spikes in the element platinum. These all testify to something extraterrestrial, probably having a role. Was it the primary cause? We don't know. But those 2 factors could have had a major role in wiping out much of the American megafauna. Now, similar to the incidents where, you know, with the meteor that impacted or killed the dinosaurs, we like, where's the crater evidence? And right, I showed you that, right? The impact is off the coast of Yucatan. People were finding the signatures of the platinum anomaly all throughout the Northern Hemisphere, and even in places like over in Australia and Southern Africa. So for those researchers working here in Europe and North America, they started wondering, well, where's the crater? Where's the evidence that there was a crater that hit 13,000 years ago? So people started looking to Greenland with all of its ice, suspecting that, well, maybe they've been looking on the wrong places all along, right? Kind of how they were looking in the oceans. They eventually looked in the oceans and found the dinosaur Chicxulub impact. Now, again, this is hotly debated, and there's a lot of data that still needs to be analyzed, and I need to do a more thorough job of continuing to read on the topic. But they have found some pretty impressive impact craters in northwest Greenland. Are they of the right age? I'm not sure, but it sort of, you know, potentially could relate. One of the theories, though, is that maybe this was not a meteor that actually came into contact and landed and formed a crater. Maybe it burst right over the surface of Earth, creating a massive sort of shock wave and heat wave that would have killed much of the life, igniting massive continent-wide wildfires. that may be one of the things that we can expect. So this is just an image of showing the crater that is under the ice in Greenland. Again, is that the right one? A lot of work remains to be determined as to whether that is. So finally, so those are the first two was climatic instability due to things like changes in the ocean circulation, thermal hailing cycle, fresh water pouring in due to the draining of Lake Agassiz, and all kinds of possible scenarios. The second one was a major meteor impact or meteor explosion over the surface of the Earth, triggering massive continent-wide wildfires that could have led to the decimation of much of life. And then the third one is what's been advanced as the overkill hypothesis. This was advanced. I need to put the guy's name in there that came up with this theory. But anyways, a leading researcher out of California back in like the 60s or the 70s put together the fact that, okay, Native Americans were arriving on the scene at least 12 to 15,000 years ago. Now we know that's at least 21,000 years ago. Maybe they had a hand in what's called the overkill hypothesis. They just simply overhunted everything to death. This is a highly contentious hypothesis. Obviously it can be, it's somewhat offensive to Native Americans. So you say, look, we don't like the idea of you speculating that our ancestors didn't have the sense to not kill everything. Did overhunting play a role? It might have. But what if climatic instability had already been the primary driver, and then you had a meteor impact or some in combination, then you put people onto the scene that could have been the nail in the coffin. In any case, we don't know who's right, but I do think it's important to know that there, again, are very hotly debated points on both sides. Some people believe that Native Americans had a profound role in eliminating these megafauna. Other people say, no, it's not possible, or, that's not likely. But what we do know, though, is that the megafauna collapse occurred roughly between 14,800 to about 13,700 years before present. And this is well before what we call the final extinctions. So this was hundreds of years before the very final extinctions of a lot of these species. And it occurred during this warm period, indicating that climatic fluctuation might have played a role. The decline predates that later cooling period we refer to as the Younger Dryas. And the decline predates the hypothesized extraterrestrial impact. So it shows that something might have been leading to the collapse before. They don't all perfectly line up. So in conclusion, we don't know. It's probably some combination of these three. And what we'll pick up now in our last 2 minutes here when we resume, we have just concluded all the material that you need to know and have in your brains 2 weeks from today when we have the midterm exam.